Hello everyone, welcome back to my channel. In previous videos, we explained the principle of KBM and MPC. In this episode, I will explain how to integrate the vehicle's KBM into the MPC algorithm and run it in Python, so you can gain a deeper understanding of how the MPC algorithm works. First, let's set the parameters. xt here equals, this is the KBM state space. So it equals fpy set f fpx and velocity transpose. All right, next xref, the reference of the trajectory equals, our goal is set the lateral offset distance from the trajectory to 0. So the fpy is 0, set f, the heading arrow, to 0, the longitudinal distance arrow to 0, and the velocity is vref transpose. And because the KBM model is used for low speed, so the vref here equals 10 km per hour. All right. Next, the three matrix SF equals diag. The FPY, the weight of FPY is 10. Set F is 10, and FPX is 0, and the velocity is 10. Okay. The weight of Q matrix goes to diag. FPY is 1, set F is 1, FPX is 0, and the velocity is 1. Okay. The last, the matrix of R goes to diag 1, 1. All right. Next, we substitute the KBM into equation 16. This equation, fpy k plus 1 given t equals fpy k given t plus dirt t times, note here, the dxm by dt is this matrix. So for the fpy, is v k given t, this equation, times sine set f k given t plus beta. All right. Next is set f k plus 1 given t equals set f k given t plus dirt t times this equation for theta f, v k given t times sine beta over lr minus v k given t times rho ref. Rho ref is the curvature of the trajectory over d times cosine set f k given t minus plus beta. Okay. Next is fpx k plus 1 given t equals fpx k given t plus dirt t times this equation, v k given t over d times cosine set f k given t plus beta. All right, The last, the last, the last one, v k plus 1 given t equals v k given t plus delta t times a k given t. All right. Note here the delta t equals 0.01 seconds, and the steps is totally 100 steps. All right. Following that is the terminal cost. Equation 14. Terminal cost. Equation 14. It goes to phi equals 1/2 times. Here I directly substitute the state x into the equation. So it goes to the n is 100. So the FPY 100 given t minus XIF. FPY XIF is 0 square. This square term is the result of multiplying the transpose of the matrix, the transpose of the matrix by the matrix itself. Then times the weight of SF. For FPY, SF is 10, so times 10 plus theta F 100 given t minus 0 square times the weight is 10 too plus I write here FPX 100 given t minus 0 square times 0 plus V 100 given t minus 10. The V reference is 10 square times the weight is 10. Okay, this is terminal cost. Next is equation 15, running cost. Running cost corresponding to equation 15. L equals 1/2 times FPY K given t minus 0 square times, let me see, the weight of Q matrix is 1 for FPY plus theta F K given t minus 0 square times 1 plus FPX K given t minus 0 square times 0 plus VK given t minus 10 square times 1. Okay. Following that is the cost function, the most important cost function corresponding to equation 13. Actually, the cost function J consists of terminal cost and running cost. So the J equals phi plus sum of L times delta t. After building the equation of cost function, we pass the cost function J to solver. solver. In this paper, the solver is C. GMRS. Over these 100 steps, the GMRS will search for an optimal sequence of steering angle. Steering angle, data 0, data 1, up to data 99, and acceleration A0, A1, up to A99, that minimize J. Minimize J mini. Ultimately, we only extract the first element from the computed sequence. Delta 0 given t, and acceleration A 0 given t. These are sent by CAN messages to the vehicle, the EPS, and brake or drive-by-wire systems. So it goes to the vehicle, EPS, or the drive brake system. Then we move into the next 10 0.01 second circle and repeat all of the steps above. Repeat again. That covers the basic principle of integrating the KBM into MPC. Now, let's take a look at how to implement these principles using Python. The first part is vehicle and MPC parameter definition. And note here, n equals 50. In the paper, the n is 100, but we use 50 here to speed up Python solving. And let's go on. Note here, this part. These QRSF matrices are the weight. The second part is Kinematic Bicycle Model, KBM. And note here, this part is state derivatives. And this is Euler forward integration. This is corresponds to the equation 16 in the paper. Alright. Part 3 is MPC cost function, which is the crucial part. And this is terminal cost equation. The last part is execute solver. And this is the inertial physical data. The lateral arrow FPY is 1.0 meter. The theta F heading arrow is 0.1, and FPX is 0, and the current speed V is 10. Alright, let's go on. Note here, use SLSQP algorithm instead of C-GEMRES. In the paper, the solver is C-GEMRES, but SLSQP is a highly mature general-purpose nonlinear optimizer in Python, so we choose to use it. Okay, let's run the code. As you can see, in the result at the 0 second, the blue line starts precisely at 1.0 meter. This matches the lateral arrow FPY equals 1.0 that we set at the inertia. Within a short 0.5 second prediction horizon, the vehicle's lateral arrow is rapidly pulled back from 1.0 meter to around the 0 line, represented by the red dashed line. Notice the smoothness of this curve. There are no sharp corners or severe overshoots. This means the KBM successfully constrained the vehicle's maneuver boundaries, allowing it to return the lane in a way that strictly follows physical laws. This plot proves that Q, R, and SF weight matrices are set very reasonably. The optimization algorithm clearly understands our intention to smoothly bring the vehicle back to the center and send the very first step to vehicle actuator, the delta and A. Alright, that covers the entire walkthrough of the integrating the KBM into MPC algorithm. If you have any questions, please leave a comment below. See you next time.